Hey guys, so we're picking up on slide 51, and this will be the end of chapter 18. It'll take me probably 3 or 4 lectures to finish it, but it'll be less than 50 minutes, and that's it. And then Friday will be your testing quiz on chapters 18, okay? All right, so delta H was super easy to measure, right? We just measured delta H because right, at constant pressure, delta H equals Q. So it's pretty straightforward. You do your very simple, very cheap coffee cup calorimetry, and you knew delta H. Well, there's not really an easy way to measure delta S. It's a lot more complicated. There are experimental measurements that you can do, but to determine the absolute value of entropy, you have to look at the variation of the heat capacity with the temperature, which means this is actually quite complicated to do because if you remember, the heat capacity is the amount of energy required to raise the temperature of a substance by 1 degree. So it gets kind of tricky, and we're not really going to go into that in general chemistry. Now, if you were to take a physical chemistry, junior level class, or go on and go to grad school and take some graduate level classes, you talk about this more. But for now, what we're going to do is I'm just going to show you that there are a whole bunch of tabulated values out there for absolute entropies of substances, and that's what we're going to use. I'm just going to teach you how to use the information that's already available in data tables, right, that are published in the back of your book and online and in a bunch of different places. But I do want you to understand where these come from. And there has to be some sort of a reference point for these values to exist. And this allows me to introduce as well the third law of thermodynamics. So remember, the first law of thermodynamics, energy is conserved, right? Second law, entropy ain't, right? Entropy's going up. The third law of thermodynamics, though, refers to entropy as well, but it relates it to temperature, okay, which is important because we have already talked about the fact that we know that entropy is related to temperature, right? Because entropy is just any amount of disorder, and as long as you aren't at 0 Kelvin, you have some energy, right? You have a temperature, which is a measurement of the kinetic energy, which means that energy has to be able to be stored in some form of vibration. So also that means that anything above 0 Kelvin has some amount of entropy, because if it has energy, then it has entropy. It has disorder because it's going to store the energy in vibrations, and then that allows it to have entropy. But at 0 Kelvin, there's no energy, which means there is no entropy. So what the third law of thermo then states, and this is a law, right? So this is not going to be broken. This is an explanation of an observed idea. And that is that the entropy of a pure crystalline substance at absolute zero is 0 because there is no temperature. Now, remember, this is based on the idea that the Kelvin scale does not go below 0. Right? There are no temperatures on the Kelvin. There are no negative temperatures on the Kelvin scale. Now, we haven't even gotten to 0 Kelvin. I mean, that is super duper cold, right? That's negative 273 degrees Celsius. And that's really hard to get to, which is why we experimentally haven't even gotten there yet. But if we ever did and somehow we found a way to go past 0, then we would have to relook at some of this stuff, right? But for now, this is what you are being taught because this is what we understand about thermodynamics. Really, all you got to do is just increase the temperature, even like 0.1. It doesn't matter, but just make it a little bit higher. And then these things have the ability, notice how they're fuzzy now instead of nice, clear, round atoms. That's because they're starting to vibrate in place, right? Because they have energy and they're storing this energy in these just little mini vibrations, right? And we already talked about this. We've looked at this as well, that temperature and entropy are directly related, and that you have this gradual increase in entropy within a phase. But when you change phase, that's when you get this really dramatic increase in entropy because you've jumped up dramatically, as far as freedom is concerned, right? Like you went from essentially no freedom to middle level freedom, So you see this nice jump, but then you see this huge jump here because you went from middle level freedom to complete freedom. You see a much more dramatic jump when we go from liquids to gases. All right, so let's look at these values then that we talked about, okay? So this probably looks similar to you if you remember the heats of formations that we talked about with delta H. And if you remember, we could take the sum of the heats of formation of the products minus the sum of the heats of formation of the reactants times their coefficients, right? And we figure out delta H reaction. Well, we're going to do the same sort of thing here with these standard molar entropies. Notice the unit, it's an energy per mole, which is why we have to multiply by the coefficients, because this only accounts for 1 mole. So if in your balanced chemical equation you have a 2 in front of something, you have to double the number, right? Which is why it's an energy per mole, also per Kelvin, right? Because entropy does depend on Kelvin. Notice the degree symbol. The degree symbol is referring to this is at standard conditions, which means standard temperature of 298 Kelvin. Which means if we're at 298 Kelvin, could anything have a standard molar entropy of 0? Any substance? And the answer is no, right? Even things that naturally exist, like diatomic hydrogen or solid lithium, these are natural substances. These have a 0 as far as their heat of formation is concerned, but they do not have a 0 as far as their standard molar entropy is concerned, because we are not at 0 Kelvin. We are at 298 Kelvin, which means they are not 0. Okay, they are something above 0. What do you also notice? They're all positive values, right? Whereas heats of formation could have been positive or negative because you could have gained energy from making them, or it could have negative, or it could have required energy to make them, which would have had a positive delta heat of formation. So you see all different types of things. But let's talk about standard molar entropies, some of the trends we see here. Right off the bat, let's find H2O. So we have H2O gas here. And as a gas, it's 188.8, but H2O liquid is 69. So what do you notice? Gases are going to have higher standard molar entropies than liquids, which are going to have higher standard molar entropies than solids in general. What are some other trends that we could pull off? Well, if you look at lithium, sodium, and potassium, what we're doing here is we're climbing our way down a column, okay, which means molar mass is going up. The London forces are going up, right? And what do you also notice is going up? The entropy, right? Because more electrons means more disorder within the molecules. Also, take a look at this. So now we're increasing mass, but you're also increasing rotations and everything else here as well, because now we can have an internal rotation in this molecule. We can't have an internal rotation in this one. So you see, definitely these jumps are relating to the fact that we're increasing the number of atoms, we're increasing the mass, but we're also increasing the number of rotations and degrees of freedom. So we see a gradual increase in the standard molar entropy. Okay. So this should look very familiar to you, right? Because we used this equation, and I've already mentioned it, to determine delta H reaction when we looked at the heats of formation. We're going to use this exact same equation, except for instead of H's, there will be capital S's, and they're not heats of formation, so it's not going to be an SF, it's just going to be an S, right? So here is your new equation. So delta S, not reactions, that means standard states, is equal to the sum of the standard molar entropies of the products times their coefficients minus the sum of the standard molar entropies of the reactants times their coefficients, right? So this general idea of products minus reactants, it's exactly the same, right? It just means we're going to be plugging in different numbers here. But the coefficients still matter, just like the coefficients mattered with our heats of formation and calculating delta H. It's just that where in this case, one of these is equal to 0, right? Because diatomic oxygen gas is standard state, so its heat of formation is 0. It doesn't matter when we're calculating delta H. It does matter when we're calculating delta S, because it is not 0 from the standard molar entropy perspective. Okay, so what I'm going to do now is I'm going to jump off this video, and we'll come back with me working things out on a piece of paper. All right, see you in the next video.